Okay, let's dive right into this explainer. Today, we're going to decode the hidden mechanics of the Cambridge A-Level Physics syllabus. Specifically, we're zeroing in on mastering circular motion on this syllabus.
We're building this from the bottom up. Here's our agenda. 1. Kinematics of circular motion. 2. Centripetal acceleration and force. 3. Orbits in gravitational fields. 4. Moving charges in magnetic fields. And finally 5. The big picture.
To kick things off, let's ground ourselves right here in Section 12 of the syllabus. We're going to start by looking at the pure kinematics of uniform circular motion.
Section 1. Kinematics of circular motion. The language of the circle. First things first, before we can understand why things move in a circle, you absolutely have to be able to define the radian. It's basically the unit we use to express angular displacement. This is your essential starting point for measuring circular paths, completely taking over from those degrees you probably relied on in earlier physics classes.
Building right on that, we hit angular speed, denoted by the Greek letter omega. Defined as the rate of change of angular displacement, this is the true measure of how incredibly fast an object is sweeping through those radians over time.
And that brings us to this remarkably elegant little mathematical relationship. Angular speed, omega, equals 2 pi divided by t, which is the period of the orbit. Think about it. 2 pi represents one full circle in radians, right? And the period is just the time it takes for that one full revolution. It's just such a beautifully clean equation.
So, as candidates, you need to be able to seamlessly link this angular speed to linear velocity using this exact formula, v equals r times omega, where r is the radius. Consider these your foundational tools, okay? Keep them right in your back pocket.
Let's move on to Section 2, Centripetal acceleration and force, the engine of the circle. Now, what's genuinely fascinating here is the very specific wording the syllabus uses to describe the engine forcing an object to constantly turn. It clearly states that a force of constant magnitude that is always perpendicular to the direction of motion causes centripetal acceleration. That rule is absolute. The force absolutely must be constant and strictly perpendicular to cause that inward acceleration. It's what constantly changes the object's direction without actually changing its speed.
You're expected to quickly recall and use both of these formulas. You can calculate the required centripetal force via angular speed, that's force equals mass times radius times omega squared, or you can use linear speed, where force equals mass times velocity squared divided by the radius. Understanding exactly how mass, radius, and speed dictate this required force is absolutely crucial for the exam.
Section 3. Orbits in gravitational fields. Syllabus applications.
Let's zoom out to the macroscopic level and see how this perfectly applies to Section 13.2, gravitational fields. Here, Newton's law of gravitation actually becomes our centripetal force. The gravitational force between two-point masses, F equals big G times m1 times m2, all divided by r squared, is literally the engine locking massive bodies like planets and satellites into circular orbits. It's the exact same circular motion physics, just with gravity stepping in to provide that perpendicular pull.
Man, when we start talking about satellites in these gravitational fields, the syllabus specifically demands you know about a geostationary orbit. The key number you have to remember here, an orbital period of exactly 24 hours.
Think of this as kind of the ultimate VIP checklist for a satellite. To achieve geostationary status, it has to meet all these highly specific criteria. It needs that 24-hour orbital period, it has to remain over the exact same spot on Earth, it must orbit from west to east, and it has to sit directly above the equator. Hit the nail on the head with all four, or it's not geostationary.
Okay, let's transition from the massive scale of outer space all the way down to the microscopic level. Section 4. Moving charges in magnetic fields, microscopic applications.
Over in Section 20.3 of the syllabus, we find yet another perfect application of these circular motion rules, but this time we're dealing with charged particles zipping through magnetic fields. Take a look at the required conditions here. You need a uniform magnetic field, and the motion of the charged particle must be perpendicular to that field. Because the magnetic force on a moving charge is perpendicular to its direction of motion, it acts exactly like a centripetal force, throwing the particle into a perfect circular path. It's the exact same concept as gravity we just looked at, just applied to electromagnetism. How cool is that?
Finally, Section 5, the big picture, tying it all together.
As we wrap up this explainer, let's look at how you're actually going to interact with these concepts on exam day. Look at page 3 of your actual paper for exam. These are the formulas you'll be armed with. Notice something? While you're given equations for gravitational potential and simple harmonic motion, you are fully expected to recall those core centripetal force equations we discussed earlier entirely from memory. You have to bring the circle equations to the exam yourself to decode these complex gravitational and magnetic systems.
So I'll leave you with this thought. From microscopic charged particles to massive orbiting satellites, do you see how the exact same rules of circular motion literally bind the entire universe together? It's pretty incredible to think that mastering just a few kinematic equations unlocks the mechanics of the whole cosmos. Thanks for joining me on this explainer, and good luck with your prep.